Welcome to this explainer on how a traditional automotive carburetor works, the mechanical magic. If you've ever popped the hood of a classic car or, even a modern lawnmower and wondered how that metallic puzzle sitting right in the center actually operates, well, you're absolutely in the right place. Today, we're going to demystify this brilliant piece of engineering step by step.
So let's dive right in by asking the core question. How can a completely simple mechanical device take liquid gasoline, mix it perfectly with air without a single electronic sensor or computer chip, and feed an engine exactly the mixture it needs to run? Well, it turns out it's an incredible, purely physical dance of pressure and mechanical linkages.
Okay, moving into section 1, the engine's diet, air and fuel. Before we even look inside the carburetor, we have to understand the basic problem it solves. An engine is essentially a giant air pump that requires a highly precise diet to generate power. There's an incredibly delicate balance required. To put it into perspective, the ideal chemically balanced mixture for gasoline is roughly 14.7 parts air to 1 part fuel by mass. If a carburetor delivers way too much fuel, the engine runs rich, which you'd notice right away through black exhaust smoke or fouled spark plugs. But if there's too much air and not enough fuel, the engine runs lean, leading to hesitation, rough running, and even dangerously high internal temperatures. So the carburetor has to constantly adjust to stay right in that sweet spot.
That brings us to section 2, carburetor physics, flow, and pressure. Let's look at where the fuel lives before it enters the engine and the fascinating physics that draw it into the moving airstream.
To maintain a consistent, ready-to-go fuel supply, the carburetor relies on a holding tank called the float bowl. This is an automatic mechanical fuel level control system, and get this, it works exactly like the float inside a standard toilet tank. When fuel is consumed by the engine, the fuel level in the bowl falls, which causes a literal float to drop. This downward movement opens a tiny needle valve to let more fuel in from the fuel pump. Once the level rises back up, the float rises with it, closing the valve. It's wonderfully simple and endlessly reliable.
Now here's the crucial point, and it comes down to a physics principle called the Venturi effect. As air gets sucked from the outside environment through the carburetor and into the engine, it passes through a narrowed section called the Venturi. Because the passage narrows, the air literally has to speed up to get through. And when its velocity increases, its static pressure actually drops. So the carburetor doesn't just mechanically suck the fuel, rather, this low static pressure created in that narrowed throat physically pulls fuel out of the float bowl through a tiny passage called a main jet and into the moving airstream, where it mixes into a highly combustible mist.
Section 3, controlling flow, the throttle plate. With the core physics of the float bowl and the Venturi effect established, we need to figure out how the driver actually commands the engine to produce more power. Actually, this is one of the most common misconceptions in all of automotive engineering. When you step on the gas pedal, you aren't directly squirting more fuel into the engine. You're actually just opening the throttle plate. The throttle is just a rotating flap at the base of the carburetor. By pressing the pedal, you open this flap to let more air into the engine. When more air rushes in, it moves faster through the Venturi, which creates a lower pressure drop, which in turn draws more fuel from the float bowl. You control the air, and the carburetor automatically matches the fuel. It's brilliant.
Let's move on to section 4, adapting to the drive, specialized circuits. Because let's face it, driving isn't just cruising at one steady speed. The carburetor features several specialized mechanical circuits to handle edge cases. For instance, let's say you need to pass someone on the highway, so you mash the gas pedal instantly. The throttle plate snaps open and air rushes in immediately. But liquid fuel is heavier than air, it has more inertia. If nothing else happened, the fuel would actually lag behind the air, causing a severe lean mixture, and the engine would stumble or even stall. To fix this, carburetors have an accelerator pump. It's a small mechanical plunger linked right to the throttle that physically squirts a quick, raw shot of fuel into the engine to bridge the gap until the Venturi effect can catch up.
Okay, but what about on a freezing cold morning? Well, a cold gasoline engine has a really hard time vaporizing fuel, so it needs a dramatically richer mixture, more fuel and less air, just to get started. That is exactly where the choke comes in. The choke is a plate at the very top of the carburetor. When closed, it literally chokes off the incoming air supply. By restricting the air, engine vacuum pulls a much higher proportion of fuel through the jets, creating that rich mixture needed to fire it up. As the engine warms up, the choke simply opens back up.
Now think about when you're just sitting at a red light with your foot completely off the pedal. The throttle plate is nearly closed. Because it's closed, air is moving way too slowly through the main Venturi to pull any fuel out of the float bowl. The engine would just die.
To prevent this, the carburetor uses an idle circuit. It uses the high engine vacuum right at the edge of that closed throttle plate to gently sip a tiny bit of fuel through a dedicated, separate passage. It's a completely different fuel pathway designed for one job: keeping the engine ticking over while you wait. Moving into Section 5, 4-stroke, creating power. The carburetor has done its job preparing this finely metered mixture of air and fuel, so let's follow it into the heart of the engine itself. The carburetor's entire purpose culminates right here in the 4-stroke cycle. First up is intake. The engine's intake valve opens, the piston pulls down, and the air-fuel mixture we just created gets sucked right into the cylinder. Second is compression. The valve closes, the piston rises, and squeezes that mixture tightly. Third is power. The spark plug fires, igniting our perfectly metered mixture, causing a rapid expansion that forcefully shoves the piston down, which is what actually turns the wheels of the car. And finally, exhaust. The piston pushes the burned gases out. Without the carburetor perfectly balancing the chemistry beforehand, this cycle simply wouldn't generate power.
Finally, Section 6, the big picture, tuning and problems. Because carburetors rely on natural air pressure, microscopic passages, and incredibly fine-moving parts, they require careful calibration.
And they can occasionally face some unique issues because this mechanical ecosystem is just so sensitive. Remember that tiny main jet the fuel flows through? A single speck of dirt can clog it, completely ruining the engine's ability to accelerate. Or a stuck float inside the float bowl could cause the needle valve to stay open, literally flooding the engine with fuel. Even a tiny crack in a rubber hose might cause a vacuum leak, allowing unmeasured extra air into the system and causing a lean condition. It's all a very delicate balance of flow and pressure.
This whole process really highlights the evolution of automotive engineering. Today, modern cars use fuel injection. Instead of relying on mechanical Venturi pressure, fuel injection uses electronic sensors and an engine control unit, a computer, to calculate exactly how much fuel is needed, spraying it directly into the engine with pinpoint electronic precision. It's undeniably better for emissions and fuel economy. But, the carburetor wasn't replaced because it was a bad design. It was an incredibly elegant, purely mechanical solution that successfully powered the world for decades, and it remains absolutely vital to classic cars, motorcycles, and small engines to this very day.
Thank you so much for joining this explainer. I really hope you walk away fully grasping the mechanical magic behind the carburetor. And I'll leave you with this exciting thought. If we achieved such mechanical brilliance without a single computer chip, what other forgotten mechanical solutions could inspire the engineering of tomorrow?